Greetings, my friends, and my name is John Gabriel, and this is the new Calculus channel. So, today I'm going to be speaking to you about the proof of a very important number theorem, which, of course, most mainstream academics have never learned, even professors of mathematics. And it's very important because if you don't know this theorem, there are many things you will not understand about radix systems and even the decimal system in particular. So let's begin. Now, what does that theorem say? That theorem says that given any rational number expressed as p over q with p over q integers and base b also an integer greater than 1, we can express the measure of p over q in base b, if and only if b, the base, contains all the prime factors of q. Okay? So, there is this misguided notion by math professors and math educators that when one writes a fraction such as a half in decimal, that 0.5 is equivalent to long division. Well, that's nonsense, and if you watch my previous video, you will see why it is nonsense. In algebra, one cannot be divided by 2, and the division algorithm only applies when the dividend is greater than the divisor. So, for example, p over q means p divided by q, and p simply goes to the top and q goes to the bottom. If p is less than q, nothing more can be done. There is no division taking place. If p is greater than q, then division, also known as the obelus division, which you see this operator here, yes, is possible. And it just simply means q subtracted from p a certain number of times until the remainder is smaller than q. And I'm not going to spend too much time on that, but you can watch the previous video and see how it works. So, much more than a simple division takes place when we write a half in the decimal radix system. Essentially, we are determining all the digits ai and di such that the number can be expressed as the sum of integral powers of this base. Okay, so the digits are an minus 1, etc. And on this side here, d1, d, etc. And all the ai's and the di's are integers, okay? So the measure of a half in base b is done as follows. We simply multiply a half by 1, meaning we're not changing its value. And then we switch the 10 and the 1 around because we are allowed to do that when we're multiplying fractions. And then we can divide 10 by 2 and we get a 5. And then all we have to do is write that 5 under the column which is labeled tenths, as you see over here, okay? So you don't even need zeros if you're carrying this template around with you. This is the radix template, okay? This means 5 tenths or 1/2. Therefore, to convert any fraction, you simply keep multiplying by 10 over 10, and you will find, if it's measurable, you will find a finite representation in that base. And now what I'm going to show you is that you can determine if a fraction p over q is measurable in a certain base. And although you could do it with any base, I'm going to show you how it works in base 10 and then prove it to you. So essentially what you have is this, okay, which represents that fraction. So now we are ready to begin the proof. And by the way, I will also put a link to this article in the details section so that you can read it through slowly and study it yourselves. So from A, we know that an equivalent fraction for any p over q to be measurable in base 10, we must have this, okay? Now, assuming that our fraction is p over q, then p over q is actually equal to this expression, yes? That you see over here, this expression, right? So, where some integer k exists such that p over q is equal to r over s times k over k, what this means is that r over s is the irreducible form, and the k's will cancel out, but it's still going to be equal to the same fraction over 10 to the power of n. So, we must note that r and s have no common prime factors because the k's cancel out. And we can end up writing the d's, as you see on this side, on the left-hand side of this equation, right? Here, where I'm pointing to, is equal to this expression here, right? And so The d's can be stated in terms of prime factors. And it follows that all the prime factors of S cancel out with some or all of the prime factors of 2 times 5 to the power of n, which implies that S must be a multiple of at least one of the prime factors 2 or 5. And that is why any fraction with 3 at the bottom doesn't have a measure in base 10. Okay, so for example, a third doesn't have a measure because S must divide, all the prime factors of S must divide 2 times 5 to the power of n. Now, and I give you some examples here, and you can go through these examples to see how it works. Now, one thing I'm going to show you very quickly is that even if you were to take the limit, so I'm going to try and write on the screen now. Let's see what happens. Screen sketch. Okay, so over here, let me use a red pen. That's good. So you see this expression over here, right? In this line, right over here. It means that 3, which is down here, because when you've got 3 at the bottom, that's all you have, must divide 2 times 5 to the power of n. And this never happens, even if you have to take the limit as n approaches infinity of 2 times 5 to the n over 3. This will never cancel out into a product of factors, okay? And you may say, well, the limit of 2 times 5 to the n over this expression here is infinite. In other words, something like this, right? And yes, that's okay, but it doesn't matter because this expression up here, 2 times 5 to the n, will never be divisible by 3, okay? So it doesn't matter if you consider the expression that you see here as n becomes indefinitely large. A third will never divide any product of 2 and 5 to the power of n. Doesn't matter how big n is, which means that there is no measure for 3 in base 10. Okay, so I'm going to leave you with that now, and I hope that you will have learned something. And if you have any questions in the comments section, just one question at a time, please, and I will answer. And so that's pretty much it. A third has no measure in base 10, and Euler was an idiot who basically defined S equals to lim S, but there is no such thing as 0.33 ... It's nonsense. Anything followed by an ellipsis is nonsense. And you can follow the discussions on sci.math to see how I correct the morons who are on that particular news group and how they refuse to accept that their ideas are wrong. Very well, my name is John Gabriel, and this is the New Calculus channel. Until next time, my friends, goodbye.